feel like, especially when I'm recording like during actual class, definitely like sometimes I'm like too close to the mic or too loud, or when I listen back to I don't listen to them much, but if I ever do, I think, oh. Plus my voice is pretty, it's even more country whenever it's recorded. It's like the redneck version of Khan Academy. That would be better than Khan Academy. That would be fun. Yeah. All right. So, so I need to back up just a little bit. So we were looking at the graph of the derivative, and my graph I'm actually going to change this minimum to like -1 so I can still see the y-axis. And I'm going to graph it again. Because this graph actually does something funny here that's difficult to see. In fact, I'm going to go over here to Desmos because Desmos is far superior to the actual calculator. And I'm going to graph our derivative here. I'm mostly doing this because this particular problem is really hard to see on our calculator graph. Unfortunately, you can't do this on the exam, but hopefully they'll give you one that doesn't look exactly like this. So you got y equals e to the square root of x over 2 square root of x minus 4. So that's the derivative that we saw. And, oh wait, this minus 4 needs to be over here, sorry. Okay, so the graph looks like this, but when we graph it on our calculator here, it's hard to see that there's that vertical asymptote there. So what's actually happening here is we have a positive derivative from 0 to this point right here, which is 0.021. And then we have a negative derivative here, and then a positive derivative again. So we have this teeny tiny sliver of time that the particle is actually going to be moving to the right because the derivative is positive here, then negative here, and then positive again. Okay? Yes. Yes, this is the derivative. Okay? So, the question asks us to tell the total distance that the particle traveled from 0 to 20. Here's the problem: it was not going in the same direction the whole time, so we can't just subtract where it's at 20 from where it was at 0. We've already found that at f of 0, our position was 6. We need to now consider these two places where our particle has a velocity of 0. We need to see where the function was, or where the particle was then. We know these 2 points are these 2 values here because we've already found where they were at rest. I did this again yesterday, but that was repetitive. We could have just used the numbers we found in A. So if I go back to my main screen, I can just do y1 of 0.0208. And it should give me this value. So f of 0.0208 is 6.07194. So just from that really tiny little time there, how far did our particle travel? 0.07194, and it was going to the right in that case, right? Yes. You could, it's just going to be units, but that's not going to be our final answer, because this is just for this little bitty time period right here. Yeah. Then we got to think about the next time the particle's at rest, because the particle is going to go to the left until it gets to 10.6386. So we're going to do y1 of 10 point, what did I just say? 6386. That's going to give us negative 11.4609. So F of 10.6386 is negative 11.4609. So we need to think about how far the particle traveled this time. So if we just subtract those two numbers, it'll give us our distance. You got 6.0. Actually, let me just do this. Let's take this number right here. Subtract this number. And we get 17.5328. So we went 17.538 units. That this time you're traveling from to the left, because you're going from a positive 6 something to a negative 11 something. And then we have already found f of 20. In part C, it was 12.5435. So this time we're going to the right. And if we subtract those numbers, 12.5435 minus that negative 11.4609, we're going to get 24.0044. There. Right. You're going to think of it like absolute value. And so whenever you're going to the left, don't count that as negative, because we're wanting total distance traveled. So everything is going to be positive, even if it's moved to the left direction. So on our graph of our derivative, which actually, let's look at the Desmos one for this particular one. So the derivative, if the derivative is positive, that tells us that our function was moving to the right. Or our point was moving to the right. Then if our derivative is negative, it tells us we're going to the left, and then it turns positive again, so we're going to the right again. So when we're looking at this graph, we can tell, like right here, we're moving to the right. Then right here at this point, we switch to left, and right here we switch to right again. But that just tells us direction. It doesn't tell us how far the particle traveled. So to know where the particle was, you have to plug into the original function. That is your position graph. So whenever you plug in 0, it tells you it was at 6. So then we need to just test those points where we have our derivative equaling 0, because that's where we switch from positive to negative. So that's where we change directions. So we tested these points to see where we're at, and then you're just looking at the distance traveled between each section. And so our answer is going to be what we get when we add all of those together. So we had 0.07 to the right, we had 17 point something to the left, and then 24.004 to the right. And we're going to add all of those together. And whenever we do that, we'll have... it's not, but it is the end of this interval that they asked us to look at. So 20 is not a 0. That's a good question. But it's the end of the interval. So that's why we started. 0 is 6 is also not a 0, but they asked us for those endpoints of the interval. Right, these two in the middle are the zeros of your derivative.
No, actually I did. Yeah. No, I actually did. How? Because that's what it was. The zeros were up and there was a number. Okay. It's called paying attention, dude. I am not.
Do not doubt, Thomas. Look, this problem has a graph. Thomas has got this.
If there was no graph, I would not have a clue about it.
Okay, so you have 4.16092 units that we have traveled. 41. Yes. Okay. Now, if we had just looked at where the function was at 0, or where the particle was at 0 and where it was at 20, we would have just subtracted these, and it would have looked like it had only moved like 6.5 to the right. That is its displacement. That's how far it went overall as far as like useful distance, but it went to the right and then left and then back right again. Yeah, displacement. Yeah. It's like whenever I'm cleaning my house and I go, to the laundry room to start some laundry, and along the way I go do something else and something else and something else and something else and forget even what I'm doing and go back upstairs, and then I realize I was supposed to be in the laundry room. The only useful distance was from where I was at to the laundry room, but my total distance that's displacement. Total distance is however far I traveled for the whole time. When we learn how to integrate, there is going to be a way. If we have certain information, there is a way that we can do that. Like we could do this problem without having to like check every point and do it this way. But we have to learn how to integrate before we can do that. So, yeah, we'll do some more to hopefully help us organize our thought a little bit more. Mm-hmm.
So you find the critical points because those are the points that it could, this is the only points that it could move, but so you have to test them all and make sure that they actually switch direction, or could it be like the same?
We looked at the graph to tell that they actually switched direction because this graph that we were looking at
But
was
it could like just touch it.
It could just touch it, but
If you didn't have a graph, you'd have to actually test it.
not necessarily, because if it does just touch and keeps on going back up in the other direction, like if it stays positive, what would happen, like let's say there was another point where that happened, it doesn't here, like at 8 or something. So if we found like an F of 8 right here, it might be negative 1.23 or something like that. So what it would do is it would just like break that amount, that 17, that where you're going to the left. It'd break it into 2 sections, but they'd still add up to the same amount. So like if you use a critical point that actually is not a change in direction, it'll still work. It's just going to break up like your sections, like you're going to move to the left a little bit and then left more instead of doing the whole section at one time.
Well, then how would you know? Okay,
8 is not. I was just trying to answer Jack's question about what would happen if. Right, it's only the points where it hits the x-axis here. He was asking what would happen if there was another one that looked like this. So, like, what if instead of looking like this, it did this, and then maybe this, and then crossed like that, like one where it touched and did not actually cross the x-axis,
Like, if it touched and then went down.
and then it went back down. It's still going to work, even if you use this point right here. You don't need to because it didn't actually change directions. Like if you're going over here, what it's going to do is like you're going to have a distance from here to here. Right. Right. It just like, it would be like if you were walking to the bathroom and you thought you forgot something, stopped for a second, but didn't actually turn around and go back, and then continued walking. Right. For the actual distance, you go back to the original position function, which for this one is that original that they gave us right here. Right. You find these critical points from the derivative. But when you're looking for the distance traveled, you're talking about position because that gives you distance traveled. Yeah. Mm-hmm. Yes, x values where the derivative equals 0. Because that's going to tell us where we change. The derivative tells us if we're going left or right by knowing if it's positive or negative. So if we just look at the original, we won't really be able to tell that. But if we look at the derivative, we can tell it was going left or right. And then we know those are the points where it changed direction. So we know we got to test those also. Total distance can be a little tricky. We'll do some more there. Okay, so 3 says a particle traveling on the x-axis has position x of t at time t. The graph of the particle's velocity is shown below from 0 to 5. Which of the following expressions gives the total distance traveled by the particle over the time 0 to 5? And, I think I was copying a problem you're going to see that's going to be multiple choice. Instead of which of the following, let's change that to right. Right, and expression that gives the total distance traveled. So that was not worded well where I copied it from. You'll have multiple choice. All right.
Your second 10.
Okay. All right. All right. So this is not our position. This is velocity. So velocity, remember, can tell us whether the function is traveling to the right or the particle is traveling to the right or to the left. Okay, so we care about our critical points. What's our critical point for this one? 2, right here. All right. So from 0 to 2, which direction is our particle traveling? Right. Because we are above the x-axis, which is positive. Which direction are we traveling? Here. Left. Okay. So, if I want to know the total distance traveled, okay, from 0, let's just look at it in sections, right? So, from 0 to 2, I'm traveling to the right. So which one is going to have the greater value? X of 0 or X of 2? Right? If I'm going to the right, X of 2 is going to have the greater value. Now, this is not position. All this tells us...
Because all this means is that you're continuing to move to the right.
Correct.
Yeah,
so this, don't think about what this graph is looking at because it is speed. It's how fast you're moving, right? So all we know for sure is that this particle from time 0 to time 2, it is moving to the right. So it starts here. It ends up over here. Yes, it would be, well, it's going to be fastest at 0 because it's got a higher velocity. So it's moving faster here and then it slows down a little bit here. But we don't really even care about speed. We just care about direction right now. So we know because we're moving to the right, because our velocity is positive, at x sub 0, particle is here. We move to the right, so it's somewhere over here. This has to have a greater value because it is on the right side. Right? If you're thinking about a number line, the bigger numbers are going to be on the right side.
The x-axis is time, the y-axis is speed.
So, if we want to know the distance for 0 is less than or equal to t less than or equal to 2, just from 0 to 2, x of 2 minus x of 0, and that's going to give us a positive value because when we're moving to the right, x of 2 has to be bigger, right? Correct. But the position is not. But that is velocity. It's asking us about distance. This is velocity.
Then what to the left be like the absolute value of x5?
Yeah, so if I'm thinking about x of 2 and x of 5, position at 2 and position at 5. Okay? From 2 to 5, my particle now, from 0 to 2, it went from here over to here somewhere. Now we're at this point. From 2 to 5, we move to the left. So right here is x of 2, right here is x of 5. Which one's going to have the greater value here? X of 2 or x of 5? 2 is on the right side.
Why?
Okay. So.
Okay, wait, are we tracking like not displacement, but distance? Because it's
where we're at. Let me just do it this way. Let's see. So what's happening?
I was thinking displacement.
Yeah. So let's make it a number line.
I don't like numbers. We're gonna. Tommy's gonna help you.
It's like a graph. Okay. So we don't know exactly where this started.
Okay. I understand it.
Okay. So we don't know exactly where it started, but let's say it started right here at -1. This is our x of 0. Right? I'm just making up numbers to demonstrate what's happening here.
Oh.
So we know this particle from 0 to 2 is going to travel to the right. Let's say maybe it ends up here. So this is x of 2. This is where we're at time equals 2. So that, knowing that this derivative is, or the velocity is positive, just tells us you were definitely moving to the right. There. So x of 2 has to be bigger than x of 0 because it's further to the right. But now, from 2 to 5, my velocity is negative, which means I turned around and I went back the other direction. So this is still x of 2. I don't know how far I go. Let's say maybe here. And I stop here. This would be my x of 5. Or it might be over here. It can be anywhere. We just know it went to the left.
Is this the number line for this graph?
It's
an example of what it could possibly be for this graph.
These numbers may not be right, but it's what it could possibly be.
How would it work out? How
Right.
is it distance?
We are not finding the exact distance because they didn't give us the equation.
Oh, yeah. But we would take the absolute value of the distance.
Right. So right here, we know x of 2 is bigger than, it's greater than, it is greater than x of 5. X of 2 has a bigger value than x 5.
Is there a difference? A difference between the total distance and the total distance?
Yes. Not always, but there can be.
What is the difference?
Okay, so like if I start here and I travel only to my right-hand side,
Yeah.
and I only go to the right-hand side,
Yeah.
then my displacement and my distance are the same. But if I start over here and I travel to the right and then turn back to the left and maybe travel back to the right again.
Your displacement time, but your total distance is the same.
No,
Total.
total distance is like how many steps she took, but the displacement is how many squares she's far away from the original spot.
Right.
Oh, so you tell me I went through physics and all the way up to here. You go from physics. No, like having them mixed up.
Right, I think so. It seems that way.
That's amazing.
So, like, if I do, to make sure everybody's with me, if I start here, this is my original spot, and if I go to the right, and then back to the left, and then maybe back to the right, and back to the left, whatever I do,
Yeah.
my displacement is just the distance from here to where I start.
Okay.
So that's displacement. But my total distance is larger than that because I backtracked. I went back and forth. Does that make sense? Sometimes they'll ask it, yes. Which is actually easier to find because you just take the original position and the final position and subtract it. Yeah. Yeah. So distance for x, for 2 less than or equal to t less than or equal to 5. We could use absolute value bars, but I think, let me look at the assignment here. But we could use absolute value bars, but I'm not going to, because we could use absolute value bars actually for both of these, and it wouldn't even matter what order we put them in. But I'm not going to do that because the answer choices on the multiple choice one that's like this don't do that. So I need distance to be positive, right? So that means I got to put the bigger number first and subtract the smaller number. So if I want to know how far I travel from here to here, x of 2 has to be first. It's the bigger number. So I would have x of 2 Why is it not working? There we go. X of 2 minus x of 5. Yes. Yeah, this is just like, it might be better to think about like my number line I put up here. I'm just trying to think about which number is bigger, because whichever number is bigger has to go first, so you don't get a negative number. Right, you could skip all of this and not really write it, and it's fine. I'm just trying to explain what's happening here. So if I want to know total distance, from 0 to 2, I go x of 2 minus x of 0. Use a bracket there, actually. Right? Plus, from 2 to 5, I have x of 2 minus x of 5. This expression here would give us the total distance that we have traveled. And the question that you'll see on the assignment that goes with this is a multiple choice question, so you wouldn't be coming up with all of that from scratch. You just have to be like kind of reasoning through which one's correct. Okay, questions?
So find a critical point and then add absolute value, or absolute, add value distance. That's from the absolute value. Wait. Yeah.
You could use absolute values here. If you did use absolute values, you really wouldn't have to think about. So like another expression you could do is you could do absolute value of x of 2 minus x of 0. And then it wouldn't matter what order. You could do x of 5 minus x of 2. If you use absolute value signs, it doesn't matter what order they're in. So, like, I could do it this way. I could do absolute value of x of 0 minus x of 2 plus absolute value of x of 2 minus x of 5, if I wanted to. Because when you put absolute value bars, it's going to make, even if you do get a negative, it's going to make it positive. But the multiple choice question that you're going to see on this assignment doesn't have any answer choices with absolute value. So you have to think about which number's higher.
Since we're only given the graph of the derivative of the position graph, velocity graph, we can only find the expression.
Right, you can't actually find the number for this because you don't have the equation. Yeah. Okay. Let's try another one. Okay, so the particle moves along the x-axis so that at any time t greater than or equal to 0, its velocity is given by this equation here. At what time is the particle furthest to the right? Okay. Now, we don't even have the original function. So we can't tell what the position is ever. We can only tell if the function is moving left or right. So hopefully we can see this graph okay here. If not, I'll resort to Desmos. I love to use Desmos. But I try not to use Desmos because you can't use Desmos on your exam. So let's type this in.
What exam was it that they used to have Desmos?
All the state exams have Desmos on them.
Oh.
And the ACT, when you take it online, has Desmos, but AP exam does not. Which AP exams are not given online. Math 1 has it.
It did?
Alright, let's see. Let's see what I got. I got nothing too. Did you do Zoom 6? Does anything show up then? Oh, I hate when this happens. This is why Desmos is so much better. Go to your table and
That's a big old number.
type in. Mine's set where it's you gotta type in. Alright, so on the table we're getting y values that are like 40-ish. So I think we have done some stuff here where our table is set where you gotta ask the numbers. If you want to change that, if you go to F2, see how you're going to change it to auto, and then it will give you the table. Make sure you hit that, and you got to hit enter, or it won't save it. Oh, gosh, I got it starting at 280, though. Ugh. Okay, let me go back and change this. Start at 0. Okay. What? Corn?
Oh, yeah, because I don't want it to be. Can I put it in the trash?
No, don't put it in that trash can. If you're going to throw it away, after we get done with notes, you can go throw it in the trash can in the lounge.
Want a piece of corn, you can just grab one.
Yeah.
Blow your nose.
Okay.
They like coated like a layer of plastic.
It's probably not pesticides. It's probably whatever. It's probably preservatives. It's probably preservatives. Even though canned corn's mostly just salt. It's probably much worse preservatives than like bread and different stuff. So, all right, we know that t is greater than or equal to 0, so I'm gonna make this 0. I'm gonna change my y max to like 60 and see what happens. On the green button and F2 is where you're going to go for your window. So I've got 0 to 10 for my X. I just left that alone. I made it, actually I made the X 0 because it tells me T's got to be greater than or equal to 0. I made my maximum 60 just because on my table I saw that. But I feel like something else is happening over here, probably. So I'm going to go back to my window and maybe make that X max 100. See what happens. Oh, I can see that it comes back down. I probably need to go further. Let's try 500.
Wait, that's not being able to touch that thing. Yeah. You only need like good. That's good. We can use that.
Okay. This probably is going to give us enough information that we need. So, it might. I want to say I remember thinking I needed to change this equation. Here's something we can do. Let's go to, yeah, this one is better, but that won't be an option. We could go back to the main screen and we could solve and type in y1 of x, because that's where it's at, equals 0. That's going to tell us where you got zeros here, and it may or may not be great, but let's hit the green button and enter. It looks like that's our only spot where we're actually crossing the x-axis, so that is helpful information. It's making me, no, this is exactly what I want. Okay, good. So, let's think about, okay, what's happening from 0 up until this point, which is 110. Okay, our particle's going to the right. What happens after that? Left. So, when's it furthest to the right? It has to be at 110 because it had to start here, over here somewhere. It had to go to the right, and then it goes back to the left forever. So it has to be right here at that point.
I appreciate that you're going to like our right and our left.
Yeah, I'm trying to.
I think that's
Yeah.
So wait, the farthest, it says farthest point to the right. So it's the highest point.
So not on. Remember, this graph is speed. So this graph, we don't care anything about whether or not it's going up or down. We care about whether it's positive or negative.
Yeah, but it says farthest to the right.
Right. So what's happening? If we think of like a sine line here.
Yeah, I know the top is to the right, but how do you determine which is further to the right? There's nothing further to the right.
So let's see, what was this number?
Oh, at what time?
5, 6, 9. All right. So for our velocity, from 0 until we get to 110.569, we have a positive, which tells us our particle goes to the right.
Oh, so the 0, like right there at 0 is the farthest to the right.
Correct.
Just move it to the right.
Right when our velocity hits 0. Because when we're looking at velocity, anytime you cross the x-axis is when you change direction.
Yeah, so
right.
The direction closer to the 0 is the furthest point on that direction. The direction
Yep. So, now we're going to have to explain this. So, we will say, since v of t is greater than 0 or is positive for 0 less than or equal to t less than or equal to 110.59 or 569, the particle moves to the right for that interval. And then we would also say since v of t is less than 0 for, I'm just going to put t is greater than 110.569. I guess really right here I probably should not have an or equal to. Right there, because it equals 0 at that point. I think that's one thing, like, probably not going to.
Not equal to 0?
Well, since I didn't put an or equal to right here, it's not positive exactly at that point, because it equals 0. 0 is neither positive nor negative. I don't think if you mess that up, I don't think they're going to, but have the rest of the reasoning correct, I don't think they're going to turn on for it. So the particle moves to the left for that interval. Therefore, the particle is furthest to the right at t equals 110.56. And thankfully this worked out here, because if this had turned back up and crossed the x-axis again, if it ever went back to the right again, we really wouldn't be able to answer this question without knowing that position function, because we wouldn't know, it went to the right, then it went to the left, then it went back to the right. We wouldn't know which one's actually furthest. But in this case, it only goes right, and then it goes left, so it has to be this point right
If we
here.
had a graph that was like, that went right 2 times, would we say we can't determine this?
In this particular case, because you don't know the original function, probably would happen is that they would give you the original function, so you would check both points and see which one had the higher value, if they had the original function there. Yes? Correct. I would probably say this would be 2 points. And you'd probably get a point for having that number correct. So if you gave that number as your answer, you'd probably get a point, and then a point for your justification. It's important that you tell which direction it's going, because if you don't, then if it was going left first and then right, it would be a totally different situation. So you have to say that. You wouldn't be able to answer when it's furthest to the right, because it would be like infinity, if that was the case. They probably wouldn't give you that.
But it could go left first, but then go right more than it. Or how does that work?
Well, like, for example, if this question said when it's furthest to the left, we couldn't answer it. Because it goes right, and then it keeps going left forever. So we couldn't really answer this question if they'd asked left.
Okay.
But they probably won't.
Yeah.
They probably won't ask left on a problem like this.
All these concepts is what.
Yeah. Okay. All right. So a particle moves along the x-axis so that at any time t greater than 0, its position is given by this equation. A is a positive constant. At what time t is the particle's position furthest to the left? We do, but it's going to be way harder, because we can't graph this. Nope, because of that A right there. We don't know what it is. Yeah, we probably could, maybe, but it's probably going to be on calculator inactive. So But when I see a question asking me for furthest to the left or to the right, that tells me I need to know the derivative and whether or not that derivative is positive or negative, so I can know whether the graph is moving or the point is moving to the left or to the right. So we're going to take the derivative of this. What have we got to use? Quotient. You could use product rule if you make a negative exponent on this. Alright, so I'm going to do x prime of t equals v of t here. So low is t. Alright. What's the derivative? Okay. E to the 2at times the derivative of 2at. What is it? It's 2a. T is your variable here. A is a constant. So A is like a number. You don't have to use product rule or anything here because A is not a variable. It is a number. So it would be, A could be 3. So if you had like 2 times 3 times t, the derivative of that would just be 6. 2. Minus, right? Yeah. All right. So I would probably factor out that e to the 2at. And I would also, no, you can't do that. Never mind. E to the 2at would leave us with 2at minus 1 over t squared. You do have to keep it, yes. Yeah. Because if you multiply, like if you distribute that back, it needs to be able to give you the same thing. And without that one, it won't do that.
Well, since it's a new semester, can we do another song for 10 points?
Yes.
Are you serious?
Do I mean that? No, I don't mean that. I said you could only do one.
Yeah, you said we can only do one.
I did say you can only do one.
Otherwise, I would have done that.
You can only do one.
Can I help? Can I get like 1 point?
No.
I have a really good song.
You can do it just for fun if you want, but there are no points. Alright, so e to the 2at could equal 0. Ooh, look at that variable.
I don't think I'll need it this semester. Last semester I needed it.
2at minus 1 will equal 0, and t squared will equal 0. So I'm setting everything from the numerator and everything from the denominator equal to 0 to find those critical points. Over here, you're just going to get t equals 0. But they told us only to look for t is greater than 0 anyway, so that is a critical point, but it doesn't really tell us a lot. E to the 2at. If I try to solve that for t, I natural log both sides, and you cannot take the natural log of 0. So e to any power is always positive. Even if it has negative exponents, it's still going to be positive. So you don't get any values from here. If you solve this for t, you would move the 1 over, so you get 2at equals 1, and you divide by 2a. It tells us here that a is a positive constant. So a is some number. We just don't know what it is. I understand why it's confusing for me to tell you it's not a variable whenever it clearly is a variable because it's a letter. It's not a variable. It's not our variable for the function. Our variable for the function is t, right? So A represents something we know is a constant number. It doesn't change, right? Variables change. Like we could put any number there for a variable. A doesn't change. We just don't know what it is. So it's a constant. So we treat it like it's a number, even though clearly it is a letter. It is a number masquerading as a letter. All right, so our critical point that we got here is 1 over 2a. So if I need to know whether my derivative is positive or negative. So I will have 0 as a critical point or the end point that I'm looking at, either one. And then I've got 1 over 2a. And I need to know what the sign of the derivative is. So I've got 3 pieces to my derivative. I've got e to the 2at. I've got this piece here, 2at minus 1. And then I've got this piece here, which is my t squared. And that will give me the sign of my velocity function. So I'm making this sign line. Now, 2 of these pieces are really easy to figure out. E to any power, I just said, was always positive. So e to any power is always positive. What else is always positive?
T squared.
T squared is always positive because you're squaring it, so it's going to be positive. 2at minus 1 is not always positive. So, the problem here is like, normally we have a 6 here, and we pick a number below 6, and we pick a number above 6, and we plug it in, and it's really easy, right? We don't have that here.
Wait, it's negative and positive. Negative.
Okay? So you got a couple options. You could do like Laura said and just like make up a number for your A, right? Say it's 3. And so like you could say it's 3 and then like have a hypothetical. Or we could think you need something between 0 and 1 over 2a. So what would be some number here that would be smaller than 1 over 2a, but bigger than 0? We can't even know that because we don't know what a is. So if a is 1 million, that would still be too big. 1/2, again, if a is 1 million, 1/2 is too big because that'd be 1 over 2 million.
Nothing can be smaller than that. That could be 1 or it could be a million.
What about
It could be 10.
what about 1 over 3a?
Wait, we just changed the 2.
Is that smaller than 1 over 2a?
Yes. I thought we were changing A.
I just need some value between 0 and 1 over 2a.
That is in fact smaller than 1.
It would be smaller, right? Because my denominator is going to be bigger there.
So it's inherently smaller.
So it's going to make the fraction smaller. So if I try that, 2a times 1 over 3a minus 1, that's going to give me 2a over 3a. My a's will cancel. 2/3 minus 1 is going to be negative 1/3. So I will get a negative right here. And so I have a negative here. It falls, we're probably going to have a positive for the other part, but if you want to really be sure of it, what's something bigger than 1 over 2a? 1 over 1a. And so that would give you 2a times 1 over a minus 1. So 2a over a minus 1. These cancel. 2 minus 1 gives us 1 more positive here. So my function's negative here, positive here. My velocity is negative in the positive. Correct, because you would be moving to the left forever. So, I mean, I guess it would be at a negative infinity, but they're probably not going to ask you that. So, our particle moves since we have a negative here, that tells me it goes left. And then since we have a positive here, it goes right. And because of time, I'm not going to write out the full justification of that. Let's, you would say that because v of t is negative for 0 to 1 over 2a, the particle moves to the left. Because the derivative is positive from 1 over 2a to infinity, the particle moves to the right. So you're going to write all that out. And then so we would say the particle is going to be furthest to the left at 1 over 2a. Actually, it was a t, not an x, wasn't it? Yeah, it was a t. Let's change that back to a t there. Because if this problem had an x in the original, it might mess you up if you put x. So try to put t there. I think more and more they're using s's instead of x's, maybe for that very reason. Yeah.
So basically what we found is that for this function, if you travel left and say you hit 1 over 2a, whatever that may be.
Right.
And then you go right.
Correct. Correct. And so you can put any number in for a. If a is 3, then the answer would be 1/6. If a was 10, the answer would be 1 over 20. If a is 1/2, the answer would be 1. It would just always be that value. It is Friday. All right. Me too. Okay, last one. Is this the last one? Okay. All right. So, particle moves along the y-axis so that its position is given here. For t is greater than 1/2. Write the equation for the velocity of the particle at time t. And then we are supposed to tell at time t equals 3 over pi. Is the particle moving toward the origin or away from the origin? Give a reason for your answer. Okay. So I believe this one is calculator inactive. I think. So we are going to try to do it calculator inactive, but we've got it still pulled up in case we get desperate here. So notice this time the particle's moving along the y-axis. So the particle's either moving up or down instead of left or right. But it's basically the same as left or right. Positive is going to be up, negative is going to be down, versus right being positive, left being negative. So we're going to treat it more or less the same.
Would the x-axis unit and y-axis unit be different in those situations? Would x knowing be time and y would be time?
In this, like in our particular case here, our x-axis is time.
Yeah.
And then we got, this is actually the y of t this time, whereas in the last problem, where it was given as x, it was still time right here, but this was x of t on the y-axis. So I actually like this better because our y is y. Instead of the x being y and the x being t. It doesn't change how you do the problem, really at all. Except you're just going to say up when you would have said right, and you're going to say down when you would have said left. Okay, so if we want the equation for the velocity at time t, we have to take the derivative of this. I'm going to rewrite it a little bit. I'm going to write it like this. Sine of t to the negative 1 squared. We okay there? All right. So if I'm going to do the derivative of this, this is not an easy derivative. So I'm going to say y prime of t. I've got two things that are multiplied together. So I have to use a product rule here. Both of those expressions have t's in them, so a product rule must be used. Which means we're going to take take t times the derivative of what's in that red box. Here's what's the more difficult part of this problem. You have to use a big time chain rule on this. So we start with this 2 that's on the outside. 2 times sine of t to the negative 1 to the first power, which we don't have to write, times the derivative of the inside, part of that, which is the derivative of sine, so that's cosine of t to the negative 1, times the derivative of t to the negative 1, which is negative 1 t to the negative 2.
Wait, whoa. I understand what you're doing, but why is it like that?
So it was, yeah, square's the first part of your chain rule, so that's this part. Then sine's the next part of your chain rule, so that's this part. And then the last part of your chain rule is that t to the negative 1, so that's this part. It's a triple chain. And we're not done, because we haven't even finished product rule. So plus sine of t to the negative 1 squared times the derivative of t, which is 1.
You know, the Ghostbusters movie came out, and I saw it. So when I saw the play, I was like, it's a really good movie.
Is there a new one?
Yeah,
Might have to watch that.
it's really good. It's actually like, if you saw the first one, it's very respectful to it. And it's like made by the director's son. So
It's been so long since I've seen the first one, I don't even know if I remember it. I'll have to watch it first.
You don't need to remember it. Like,
Yeah.
you saw it, you go.
Alright, I'm going to change all of these t to the negative 1s back to 1 over t's. Just because, let's put a negative here. And that t, let's go down further actually. I can actually, if I want to here, cancel this t with one of the t's here. And so this is my velocity function. It's crazy. You could have on this, yeah, you could stop on the first step. It's just going to be easier to do part B if we have it looking like this instead. But you could stop there for that first step. I know. Yeah. Yeah, I know. Okay.
So now is the second part you just plug 3 pi in?
Okay. So now we need to plug in 3 over pi, kind of. We're not going to be totally done after that, but let's do it one step at a time. So I plug in 3 over pi. I'm going to have negative 2 sine of 1 over 3 over pi. Cosine of 1 over 3 over pi. Over 3 over pi. Plus sine squared of 1 over 3 over pi. Okay, this is calculator inactive. But what is 1 over 3 over pi.
It's just pi.
Okay, 1 times pi over 3. So it's just pi over 3. So we've got negative 2 sine of pi over 3 cosine of pi over 3. You could have gone straight to that if you wanted. Over 3 over pi plus sine squared of pi over 3. So now we're going to pull values from the unit circle that we all know and love. We might need a second semester quiz on it. Pi over 3 is right here. X coordinate is 1/2. Y coordinate square root of 3 over 2. So it's going to be negative 2 times square root of 3 over 2 times 1/2 over 3 over pi plus is going to be square root of 3 over 2 squared. Whew. Okay. This is going to be, let's see, I'm going to cancel, this is like 2 over 1, so I'm going to cancel this 2 with this 2. We're going to get negative root 3 over 2 divided by 3 over pi plus 3/4. And that's going to be negative root 3 over 2 times pi over 3 plus 3/4. So I got negative root 3, I'm going to put the pi out here, over 6 plus 3/4. I don't know what value that is, but remember we're thinking about velocity here. So what we care about is whether or not this is positive or negative. So pi, what's pi's approximation? Okay, square root of 3. 1 point something. So, shoot, usually it's a little easier to tell for sure. I think it's going to be negative, right? I'm gonna have to cheat. Usually it's a little more obvious than this, but I've made up this problem. I know. I just want to really make sure. Yeah, it is negative. All right, so if this is negative, what does that tell us about? It would be left if we were going left and right, but it's on the y-axis, so it's going up and down. So instead of being left, it's going to be down. All right, so I'm hearing you guys tell me it's moving away from the origin. Okay, let's think about this. All right, here's our y-axis. Okay, so this tells me particle's moving down. All right, if I start from right here and my particle moves down, is it moving towards the origin or away from the origin? Okay, what about if I start right here and it's moving down? It's moving away. So this information alone is not enough to answer this question. We need to know where it started at. How do I find where it started at? Plug it into the original function. Okay? 3 over pi, because that's the point we're looking at. Alright, so y of 3 over pi. If you have ran out of room, I'll post the video. T sine squared 1 over t. Is it okay if I go ahead and flip this to pi over 3? Because when we do 1 over 3 over pi, we'll get pi over 3. Alright, so this is going to be 3 over pi times pi over 3 is root 3 over 2 squared. Is this positive or negative? It's going to be positive. So, which situation do I have? The red arrow or the green arrow here? Red. Because I start above the x-axis, I'm putting positive, but I'm moving down. Okay? So, you would say since y of 3 over pi is greater than 0 and v of 3 over pi is less than 0, the particle. It's only asking us about this one single point at 3 over pi. So it is possible that this answer changes after 3 over pi, but it only cares about this one point. It's toward the origin. Now, the last two were difficult equations to deal with. The ideas, though, I'm hoping are coming through clearly, even if you're having a little bit of struggle with the equations. Okay. So, the assignment that we're having, I'll get to the other thing I was going to do today. I have to adjust. I'm already behind for only 3 days into the week. We were much more efficient today.
We're thorough this semester.
Okay. Pass one. Y'all pass one over while we're reading that. Oh, wait. Hold on. Jack already has it.